But anyways, you'll see a little differently how it comes into it. Okay, so arc length and curvature. So if you guys remember back in Cal 1, maybe Cal 2, about arc length, and most of the time, your professor always told you just write it in the integral format and don't bother integrating because the integral is just too hard to deal with. And right, you just left it and just called it a day. If it was some easy type of integration, you could do it, but most of the time it's just too difficult to do without, without some tools or some tricks up its sleeve. But before we get there, what does it look like in R space, right? In space itself. So let's suppose I have this nice, beautiful curve, like a roller coaster there. Okay. Now, arc length, in theory, and this applies to two-dimensional as well, is essentially if I'm picking 2 points on this curve here, and I'm connecting them. And I'm doing that over and over and over again. So essentially we have something like this going on. So I have all of these line segments that kind of represent the curvature. Obviously, it's not perfect because they're line segments, right? And it's not a curve itself. But the theory behind this is, well, if I find the sum or sum up all of these line segments, we get the curvature, or we create a curve. And if we take the limit of all of these portions, we get the length of the curve. Okay. Now, I'm not going to spare you too much of the crazy details, but eventually, just like it was in two-dimensional, the length of the curve is represented as the integral of the distance from one point to the other point. Now, because we're in space, we're not taking the integral of just a line anymore. We're taking the lines of multiple lines, or a three-dimensional space. So the curve length is equal to the integral from A to B of the derivative of each component squared and divided by its square root. Or if you really want to break it down, it's just the integral of the magnitude of the derivative. Hence the reason why I say hopefully you like derivatives or integration, because we were doing a lot of this stuff. So in most cases, we're going to be using this no matter what, because that looks like a horrible mess anyways, right? And the nice thing is it gets rid of the square root because it's incorporated into the magnitude itself, right? So it's nothing really brand new we've seen before. Now we're just applying it to its length. Now, since we have an equation for length of curves, let's now apply it. So find the length of the arc of the cylindrical helix with the vector equation of r of t is equal to cosine t, sine t, and t from the point 1, 0, 0, 0 to 1, 0, 2 pi. Okay, so just like previous sections, it's hinted. That's the t variable, x, y, and t. So if I follow this curvature format, we're going to find the integral of 0 to 2 pi of this vector, or the arc, or sorry, arc, I will keep saying arc length, of the magnitude of the derivative vector with respect to t. So first, we got to find the derivative. All right. The derivative of cosine is negative sine. I'll do this, keep forgetting. The derivative of sine is positive cosine, so it'd be negative cosine. And the derivative of negative t is just -1. And now we're going to find the magnitude of it. And this goes back to some pre-cal way back there, right? Sine squared plus cosine squared. Everybody hopefully it kind of remembers that one. That's a nice one. And look at that. How beautiful is that? Our magnitude is the square root of 2, which is great because it has nothing to do with t, right? So therefore, our integration is going to be so much easier to deal with, because now we're just doing the integral from 0 to pi over 2 pi of just the square root of 2 dt. How lovely, right? So this ends up giving square root of 2t evaluated at 2 pi and 0. So 0, right? So it's just going to be 2 pi square root of 2. Don't you love questions like this? Yeah, no, too easy. Want something harder? Yeah, that's it. You guys want harder questions, right? Yeah. Okay. So now that we have that curve lengths, and it's not too difficult to deal with, let's do something else. Why don't we parameterize some stuff? So the problem we have going on is, oh, good, I'm glad. Yeah. Since the curve can, so here's the problem we have, as you guys noticed. Since a curve can be represented as multiple vector functions, right? So given another point, I can have another vector respective to that, and then find its respective vectors. So the question now becomes, well, which one's true? What is the actual arc length of here to here given a specific vector? How are we always going to get the exact same answer and not a different one depending on the vector we use? So this is what's called a parameterizations of curves. So all we're going to do is, given some vectors functions that have the same length, that means that we have the function that represents or another function that is created from this. So it's called the arc length function. So these are all the arc lengths given any vector along this curve. Okay? And it's denoted like this, where instead of t now is represented as u. Now, before we get into the concepts of what I mean by arc functions, again, like everything else, let me show you what's going on. Maybe that'll be a little easier explanation to go by from there. All right, so let's go back to our simple, that's bad. Portion there. And again, we have this curve, let's say doing this, for instance. Now, curvature. Curvature is going to be a little different than arc length. Okay. Now, when it comes to the arc length functions themselves, okay, don't worry too much of this equation. It's just a general rule applied to this. Okay. Essentially, it gives you arbitrary all the arc lengths you actually have. Okay. However, when it comes to curvature, we're going to see what the curvature is at each particular length. So if I go over here, what's this curving? How is this curving going this way? Is it curving that way, this way, that way, and forward? So I have every arbitrary one. As everybody can see, it curves here, right? And it gives a nice curve here, and also curves there. Now, here's the interesting part. If I'm given a point, and let's suppose I have a lot of different points on this line or this curve here, right? Just give arbitrary points on this portion. And what we're going to do is we're going to take the unit tangent at every single point we have. Remember, so that means every single point we have a different unit tangent, right? Because remember, tangent means actually perpendicular to it, right? It's a tangent to it. So like this is going to be the tangent line. So the unit tangent would just be looking like this, right? It's perpendicular to the actual line. And if I just keep going at that, I get something like that. Now, just in case you guys forgot, we just did it, but just in case. The unit tangent is represented as this equation. And if I want to see the curvature using unit tangents, as you can see, the arrows kind of tell me the direction of the curve. Because if I see these three here, well, that means the curve is going up. And then at this point, it kind of flattens and it goes down. And it keeps going down, then it kind of flattens and then it goes back up. So essentially what the theory ends up being is, well, if I want to find the actual curvature of any type of curve in space, I can just graph its respective tangent unit tangents, and that shows me what is curving or bending, kind of like slope fields when it comes into calculus. That same logic comes into play here. So the unit tangent is a key thing because it tells me one very special thing. So the tangent shows the change in direction of the curve. So you may kind of hint how to find the curvature without, kind of looking at this already. So we have two different things. We have a smooth curve that has no sharp corners or cusps. So when the tangent vector turns, it does continuously, meaning the curve is smooth if the derivative is continuous. Sorry. So the same rule applies, right? So if I have like doing this as some curve doing that, the derivative does not exist there because the general rules don't exist, right? So derivatives don't exist at corners, cusps, and undefined values, right? So that's the main focus. The same thing applies here. The good news is, for our cases, we're always going to be dealing with nice smooth surfaces and curves in space. So, most of the time you'll be seeing that itself. But technically, there is a way of doing that. Okay. So let's talk about the curvature now. So at a given point, it is the measure of how quickly the curve changes based off its tangent and the magnitude of the rate of the change. So therefore, we kind of have a definition of the curvature. Because it shows me the direction of